So now let's prove this Butler theorem basically shows that positive definite functions on the group corresponds to the integral of characters, okay, against some positive measure, all right? I made a mistake from last time. I should mention this mu has to be greater than 0, of course, all right? So the idea is quite simple, okay? So if you want to find some measure and show some function is equal to the integral against this measure, this is essentially just using the dual theorem, okay? So the Riesz representation theorem tells you if you can you can realize this as a linear functional, then this integral, well, this functional is always integrate against a measure, okay? That's kind of the idea. So because let me just maybe write it here. So the idea is that to find a measure on the G hat, the dual group, because that's identified as the C0 of the dual group, this conjugate. Okay, so I basically want to find the bounded linear function on C0 of the G hat. Well, but C0 G hat is kind of difficult to study, but I do have a dense subalgebra when we talk about the Fourier transform. It actually contains the Fourier transform of the L1 of G. Okay, so all the Fourier transform of L1 functions are in C0, and using some Galfand magic, we saw that this is going to be dense in the C0. So well, this is not equal to the dual, but inside the C0. Okay, so this is inside the C0 of the G hat. So essentially what we want to do is that we want to define something on the L1, the Fourier transform of the L1 function. And then I will try to make it, say, function on the C0 of G hat. Okay, so that's kind of the idea. Now let's start the proof. So without loss of generality, let's just assume that this phi of E is going to be equals to 1. So phi as a function in the L infinity space is the infinite norm is equal to 1. All right, so because phi is inside the L infinity, well, that's identified as the dual of the L1 of G. So I can define the following. So let's define for, say, T of phi that maps the L1 of G to C by integrating against phi. Okay, so T phi given an L1 function, that's just equals to the integral of f against phi dx. Okay, the left power measure. Okay, because phi is an L infinity function, this is T phi is in the dual space of L1. So T phi is the L1 of G dual. And moreover, the norm of this T phi by this identification. So this is equals to the subnorm of your phi, which is equals to 1. Okay. All right. So now let's define some inner product-ish thing on the L1 of G. Okay. So let's do the following. So now let's define this notation. Let's say FG bracket. Okay. I define it as I do the T phi of the F convolute with the involution of G, okay? So here, again, the involution of G is basically G of X inverse, the whole thing conjugate because everything is abelian, so modular is equal to 1. All right, so now, in other words, I can write this out. This is essentially just integrating this convolution function against my positive definite function phi. And then we have seen this calculation many times, so you can expand it. Okay, so in the end, this is going to be equals to following. This is equals to the fx gy bar, and then you do the phi of xy inverse dx dy. Okay, I'm skipping some calculation here. All right, this is essentially, I have done this multiple times when we talk about the equivalence of multiple equivalence condition of the positive definite functions. Okay, so do some left translation. All right, so what you can see is that, well, because I have this formula, if I want to evaluate this bracket f with f, okay, well, this is essentially just integrating against this f with f check. So this is integrate f against f check, phi x, okay, dx, all right, This is going to be positive, okay? This is one characterization of a positive definite function. You can also see it from this double integral as well. But anyways, you have something that's positive. And you can also convince yourself the following. If you want to reverse this f and g, so you do the reverse. Well, because you have this formula star here, then if you change the f and y, then what you need to do is you take the whole thing conjugate, okay? So they are actually the same, okay? So you have something like, looks like a Hermitian form. And this one is also clearly linear in your first term. So if you have, so this fg is going to be linear in f, okay? So if you, of course, you replace, again, by the star condition, you have it's linear in f. So because it's Hermitian, it's going to be conjugate linear in the second space. And you have this ff greater than or equal to 0, so that just means it's a sesquilinear form, okay? One way of saying it is that this is a sesquilinear form. If you don't know what it is, it's essentially just a pre-inner, looks like a pre-inner product, okay? Let's see, exactly linear in the first one, being Hermitian, and if you take two things, you have something non-negative, okay? So that's sesquilinear form. And whenever you have a sesquilinear form, the good thing is that, well, technically you can do an inner product-ish construction. But second of all, you can also have the Cauchy-Schwarz inequality. It always holds, okay? So by the Cauchy-Schwarz, you always have that if you do f and g, they're kind of the inner product-ish thing. It's bounded above by f with f and g with g, okay? The product of these two, all right? So now what you can do is that, well, so suppose, because here f and g are arbitrary, so you can let your g to be some approximate unit, let's say phi alpha, approximate unit. So from your assignment, you can make these phi alpha satisfy some really nice properties. So for example, you can like phi alpha, the support of the phi alpha goes to the infinity. You can also make phi alpha x equals to phi alpha x inverse as well, okay? You can put in some nice properties. But if you do that, if you consider what's phi alpha with phi alpha in your bracket, okay? So this one by the star, again, this computation we did before. So you have a phi alpha of x, you have a phi alpha of y, and then you have a phi of, well, I should say psi alpha x and psi alpha y inverse, well, conjugate, and you do the xy inverse, dx dy. And because your psi alpha, the support, is goes to the identity, so, and your phi, your positive definite function is, well, is going to be continuous at identity. So this whole thing is going to converge to the phi of v, okay, which by our assumption is going to be equals to 1, okay? So what you show is essentially the following. Well, on the other hand, this f convolute with this phi alpha, that's actually just going to converge to your f. And because your t phi, this linear functional against integrating against this this phi, is bounded linear functional on L1, so the t phi of f, okay, so this is one is going to be equals to the limit of the t phi of f of psi alpha. That's because the right hand side is converging in L1, and then you apply something continuous on L1. Okay, so this they have to be the same. And this one is going to be bounded above by the f with f, okay, to the half. Okay, you take the limit, and then you have the psi alpha with psi alpha to the half. Okay, that's by the Cauchy-Schwarz inequality. But when you do the psi alpha with psi alpha, we show that's converging to 1. So this whole thing is going to be bounded above by f with f to the half. Okay. So what is ff to the half is essentially the following. So if you let h to be f convolute with f involution, this is essentially just t phi of h, okay, the whole thing to the half, okay? All right, so now we can do a little bit more than that. Okay, so if you basically repeat the same trick, okay, then if you say let's say Hn is equals to h of n minus 1 convolute with h of n minus 1, okay? And let's start with the first one is just h. So h2 is 2 of h convolute together. H3 is going to be 2 of the h2 convolute together. And because your definition of h, you saw h check is equals to h. Okay, so you can say h2 is essentially just h convolute with h. And H3 is going to be H2 convolute with H2, so basically the 4 of them convolute together, so 4 of them. And you can say, well, Hn is essentially, you have 2 to the n minus 1 copies of H, they convolute with one another. But in any case, this H is going to be in L1 anyways. All right, so now I have this T phi of this F. Okay, this is going to be bounded above by the T phi of H to the half, and I apply the same trick to H again. So I have this is less than or equals to T phi of H2, but now I have another half, so I have a quarter here. And then you do the same thing over and over again. So what you have is less than or equals to T phi of Hn, the whole thing to the power 1 over 2 to the n, okay? Well, what is it? Well, this is because T phi has norm 1, so this is going to be bounded. So what we prove is essentially for every n, I have T phi of f is going to be bounded above by the 1 norm of the Hn, of course, raised to the 1 over 2 to the n. Okay, so I have Hn is 1 norm to the 1 over 2 to the n. But what is Hn? Well, that's equals to the h convolute 2 to the n minus 1 times the whole thing to the 2 to the n, okay? And we have a little formula when we talk about the Fourier transform. Basically, we'll say if you have a function in L1, then its Fourier transform in L infinity. Well, that's going to have an infinity norm, which is less than or equals to 1 norm, but actually equals to the spectrum radius formula. So let's just recall. We proved that the f check is infinity norm, or in this case, I should say h check. That's going to be equals to the limit as n goes to infinity of h convolute n times to the norm, and then I put it 1 over n's power, okay? So this is coming from the Galfand theory. We didn't prove it, but that's just a fact. So now you look at this formula, you have h raised to the 2 to the n minus 1 power and n goes to infinity. So you see that this one is related to the norm of the h check, okay? So it's the infinity norm, in fact, raised to the half power, okay? And because your h check, well, your h is just equals to the convolution of 2 copies of f, okay, f and f check. So if you do the convolution, okay, this is essentially just the f check, the whole thing square, okay? This is by the convolution is going to be a respect to your star convolution and involution, your Fourier transform respect to your convolution and involution. So because of that, this h hat, the infinity norm, is going to be equals to your f hat, the infinity norm squared, so the half cancels, okay? So this is essentially the f hat to the infinity norm. And now you see why we define it this way, okay? So this T phi, I treat it as a function on the CZ, on the L1 function, but then I can also treat it as the Fourier transform, okay? I pretend this T phi maps the f hat to the corresponding value T phi of f, okay? So let's pretend now this T phi maps from the Fourier transform of the L1 of G to C by mapping this f hat to T phi of f, okay? And if you do it this way, well, you do have something that's norm decreasing, okay? This T phi, the norm is bounded above by 1, okay, because we just proved T phi of f is bounded above by the infinite norm of f hat. And in fact, that also shows things are actually well defined, okay? So because of that, well, now your Fourier transform of the L1 of G is dense in the C0. We showed that before. So this is contained in the C0 of the G hat. And we know this inclusion is also dense. So basically we extend, because your T phi is bounded, you extend it as a functional from the C0 of the G hat, okay, to C by mapping the Fourier transform of L1 to the corresponding T phi. You can extend continuously. So you have this T phi is in fact inside the C0 G hat, the dual space, okay, which is isomorphic, can be identified as the measure space on G hat, okay. So now because of that, and you also have this T phi is less than or equal to 1. So by the Riesz representation, now you have a measure on your on the measure space of the G hat. So that first of all, your measure, the norm of your measure is also less than or equal to 1 because your functional is less than or equal to 1. And this T phi of this f hat, or this f, this value, okay, that's going to be equals to the integral of your f hat against this mu, okay? So what is this? Well, on the left-hand side, this is essentially just saying the integral of this f with the phi of dx is equals to the integral of your Fourier transform against this mu. Well, what is it? Well, let's just expand the right-hand side a little bit. So on the right-hand side, well, this is the integrate over the G hat. So this, I'm plugging in a dual element in the dual group or a character. So this mu is mu of phi. Okay, so what is the Fourier transform evaluated at phi by definition? So this is, let's just write it out. So this is the integral over G of the fx, integrate against the fx bar or the phi x bar or phi x inverse dx, and then I have a d mu of phi. And well, now you want to pull out the phi, so this is going to be equals to the integral. Let's exchange the integration. So let's make the f of x go outside, and I do a integral of a bunch of phi x inverse or phi x bar dx, or d mu of phi. Okay, so I do the integral over phi first, and then I do dx. All right. Well, now you compare these two integrals. Well, on the left-hand side, you integrate f phi, and on the right-hand side, you have f with this integral. So by Riesz representation, they have to be the same. Okay, your phi is in the L infinity, that's in your dual. So this basically shows that the phi of x has to equals to this integral of the phi x bar, d mu of phi, okay, for some measure mu on your G check, okay. Let's just pretend, well, technically this is equals to the integral of phi, the mu check, but let's just pretend the mu check is the measure we found in the first place, okay? So this, I basically now find a measure. This is the mu check, okay? So that's going to be the measure. I realize my phi of x, this positive definite function, as an integral of some character, okay? Integrate the character against some measure on the character space or the dual group, okay? Well, now I just need to show this mu check is positive. Well, why is that? Well, because first of all, this phi of e, if I just consider phi of e, well, this equals to the integrate of phi of e, let's do the mu check, so I don't need a conjugate there. So this is d mu check of phi. But character on the identity is always equals to 1. So this one is always equal to 1. So this evaluate to mu check of the G, which by our assumption, this phi of e we chose so that phi of e is equal to 1. So the mu check, when you measure on the entire G, that's equals to 1. So mu check of G is going to be less than equals to the norm of mu check. Okay, the mu check of a set, you do the Jordan decomposition and you sum up all the positive part. Okay, so of course, mu check of G is less than equals to its norm. But this one, we know mu check is less than equal to 1 because of the functional is less than equal to 1. Okay, this mu check come from the functional, so mu has norm less than equal to 1, mu check also less than equal to 1. So they have to be the same. Okay, so this implies that the mu check is essentially just equals to mu check of G, G hat. Okay, I should say G hat here. And they have to be equals to 1 anyways. But if you have a measure, its norm equals to the mu of the entire space, well, it just means it has no negative parts. Okay, if you think about it, if your Jordan decomposition has any negative parts, okay, then you have something, of course, that cannot equals to this this mu check of the entire space cannot equals to the norm. Okay, so that just implies your mu check is greater than equal to 0. Okay, so the mu check is the measure you're looking for. Okay, and we finish this proof.